Hi there. Today we'll look at Rethinking Attention with Performers by researchers of Google, the University of Cambridge, DeepMind, and the Alan Turing Institute. This paper is yet another paper in the quest to make transformers more performant. And what better name to give to a technique than the performer? So the performers are a new kind of class of models. They try to approximate the transformer. If you don't know what a transformer is, I've done like a ton of videos on transformers, on attention mechanisms, and you can, there's more than enough material to look that up. Today, we'll talk about performers. And the performers, as I already said, they approximate transformers, and they do so without running into the classic transformer bottleneck, which is that the attention matrix in the transformer has space and compute requirements that are quadratic in the size of the input, and that limits how much input you can put into the model. So it kind of limits how long of text you can input if you work with text, or how big your images are that you can work with. This is all kind of bad at when you use transformers. So the performers get around this by this technique they call fast attention via positive orthogonal random features, abbreviated favor plus. They use this favor plus to get around it, and what's interesting is that the favor plus, I'll just call it favor, this fast attention, it is potentially useful beyond transformers. So it's apparently been here developed in the realm of the transformers, but they say, which may be of independent interest for scalable kernel methods. You'll see what they do is they approximate the attention matrix by decomposing it, but they do it in a special way. And they do it in the way, if you know what random Fourier features are, maybe you can kind of think ahead a little bit. If not, we'll get into it for sure. I think, honestly, this might be enabling one of the next mini breakthroughs in deep learning. Not big breakthrough, but kind of mini breakthrough. I remember a time when we used sigmoid and tan H nonlinearities. Believe it or not, you young kids, at the beginning of not the beginning of deep learning, but before deep learning really took off, it was the sensible thing to use softmax and tan H nonlinearities everywhere in your neural networks because, well, first of all, they were like differentiable, so that was cool. And then, it was sort of how nature does it with the step function it was an approximation to the step function in a true neuron and so on. And it was just kind of well motivated. So people thought that must be the way to go. But then, of course, turned out that ReLUs are much easier, much more stable, give much better results and so on, don't saturate, all of these cool things. This here is kind of it feels like the same thing, because right now we're doing this softmax thing in attention. And it's very important because it normalizes the attention matrix, right? It gives you kind of this thing that comes out as kind of a distribution over the inputs and so on. So it's well motivated, and you may be able to see. But also, as the sigmoid is, it's kind of has this exponential thing in there. And the favor algorithm is going to approximate this softmax thing. But it can be used to approximate much more. So maybe, we're going to find that if we swap out these the nonlinearity in there, we might be able to build much better transformers, or whatever the model will be called, performers, I guess. They already do this here with ReLUs in this very paper. So the performer is going to be fully compatible with regular transformer and with strong theoretical guarantees, unbiased or nearly unbiased estimation of the attention matrix, uniform convergence, and low estimation variance. So the difference of the performer here is going to be that there have been methods before that decompose the attention matrix into low rank matrices, but those either don't work, or they kind of rely on priors, like you're assuming that your attention matrix has a certain structure. If it doesn't, it sort of fails. This method here is going to be an unbiased estimator, and it's going to sort of converge to the attention matrix if you add more of these random features. Okay, this is fed here, like provably not relying on any priors, fully compatible with regular transformers, which means that you can take a transformer checkpoint and sort of plug it into this framework, and then you just have to fine-tune a little bit to sort of use the checkpoint of a regular transformer, which is pretty cool, right? So we'll go through the paper. It's quite a heavy paper. It's quite a math-heavy paper. We won't go through all of it. I just kind of want you to get the idea of what these performers do, what the reasoning behind it is, and how you might be able to kind of work with them or extend them where it's going from here. As always, if you like content like this, don't hesitate to share it out and tell your friends about it. All right, so the problem with attention, or the problem with transformers, is, like, I've done this a million times and you can go look it up, but if you want to map a sequence of layer L into a sequence or a set or whatnot of layer L plus 1, and you need to compute these attention weights, right? So the attention weights are going to be from each token here to each token in the next layer. You're going to compute one of these weights, right? So there is this matrix is called A, the attention matrix, and A is going to be of size L by L. And that is a problem if you have long sequences, right? You can already see this. So the way that this A comes to be is that conceptually the upper layer, like it's all the same layer, but conceptually the upper layer emits something that are called queries, and the lower layer emits something that are called keys and values. Now, the keys and the queries, they go together into matrices. So you would multiply the keys and the queries. Then you run this through, and this is the problem, you run this through a softmax nonlinearity to basically get a distribution, and then you multiply it by the values. So the query key matrix, this attention matrix, it will tell you how to aggregate the values. All right. If it weren't for the softmax, so you can think if the dimensions of the queries and keys and values, let's call it small d, then the dimensionality here would be something like, here you'd have L by D, here you'd have D by L for the transposed, and then here you'd have L by D. So because you have to do the softmax, you have to compute this first, which gives you this L by L, which is the terrible thing. However, if you could somehow decompose the softmax operation, you could first do keys and values, which will give you a D by D matrix, and then you could multiply it by the Q matrix, right? Which would be much, much, much more easy if D is smaller than L. Certainly it wouldn't grow quadratically in L, it would just grow linearly in space and time. So here, this is formulated out. The attention mechanism right here, the attention mechanism is made of queries, keys, and values, and it's given by this formula right here. Now, there is a bit of a technicality. I wasn't exactly correct in what A is. So here they say I called this thing here A. Okay, they are very specific what they mean by A. By A, they simply mean the exponential function of the normalized queries times keys, and then to get the actual softmax, you have to normalize by here. So D, which is, so you see the inverse is made here. D is constructed from A and normalizes A. But the normalization is of secondary importance. The important part here is that this exponential cannot be easily decomposed, right? It's not like you can decompose the inner multiplication into 2 exponentials or something. Otherwise, the problem would be solved. So, what is this paper doing? It's exactly what I just said was impossible. So you have this matrix A right here, and you multiply it by V. I guess, again, forget about the normalization by now. It will decompose A into the Q prime and K prime. Now, they are called prime because they are not the queries and the keys, because we've just said the queries and the keys, they go into the exponential. So it's going to be that Q prime times K prime transposed is going to be approximately equal to exponential function of Q times K. Maybe normalized by square root of D. But you can see that this here isn't decomposable, and yet they decompose it. And the question is how, because there have been papers before that try to decompose the attention matrix. I think Linformer maybe, and there is also the Reformer, which uses LSH and so on. So there have been a number of tricks, but they all don't perform as well, which this paper also shows empirically, and they all rely on certain assumptions of the attention matrix, and they all are not unbiased estimators in general. This paper is going to be an unbiased estimator, and they do this via sort of a kernel framework. So what they first of all, they make this problem more general. They say we have our attention matrix A, the ijth entry is going to be the query I, the key j, and some kernel function of that. Okay? In our case, this is going to be the x of query times key, like this. Sorry, the other way around. Query transposed, query times key, the inner product of that. However, you can think of any sort of kernel function. Okay, so yeah, if I'm not going to try to explain more details into kernels. We had a fantastic machine learning street talk. So if you don't know about this is our podcast, Machine Learning Street Talk, where Alex Stanlek explained kernels in great detail and with very, very precise language and very understandable as well. So what I'm going to say is that they allow you to do things like this. So you can think of kernels as kind of connecting two things. They represent an inner product in some other space. Okay, so the kernel function of two inputs right here will be equal to some inner product of the two inputs when pulled through this function phi right here. And that's what we're going to use. Now, usually when you learn about kernels, you do it in this way. You say, we would like to compute in this very high dimensional space, but we can't. We can't do inner products. We can't map this function phi explicitly. So we're going to instead use this kernel right here, this kernel function. And that's going to be equal if you pick the right kernel function for the particular phi. In this paper, we're going to do it the other way around, because we say, well, this thing here this is the softmax function, and that's just a beast, right? We can't possibly compute that. However, if we could find out what inner product that corresponds to, what other space, we could just go to that other space and perform an inner product. And this thing over here is linear, right? This is a linear function. This here is the nonlinear function. This is our softmax. So you can see that by going in this way, by finding what is the higher or the phi function for the softmax kernel, we can construct all of this attention business in a linear fashion. And that's what this paper does. And what it allows you to do is it allows you to find these Q and K, Q prime and K prime matrices, such that as over here, right, this is the kernel function, and this here is linear. And then you can simply first multiply K by V, or K prime by V, and then you can multiply Q by K, and that will alleviate you of having this giant attention matrix. So how do they do it? If you know about random Fourier features, this is going to be very much or very similar thing right here. They're not going to explicitly construct the high dimensional space such that this is exactly equal, but they're going to construct an approximation. And the approximation you can make arbitrarily good. And you do that via the following. You say, so here you see, this is how do I have to map something into this other dimensional space where this whole softmax business is just a linear operation. So what you would do ultimately is you would take your queries, you would map it through this phi, okay, and you would take your keys and you would also map it through this phi, and this will give you query prime and this will give you key prime, right? So, and then in the higher, lower, whatever dimensional space, you would take the inner product, and the inner product between the two is going to approximately be as if you had so the inner product is going to be approximately as if you had taken the original Q and K, multiplied them, and put them through a softmax. How do we do it? So here we define what the function needs to look like such that this holds. The function, again, they go very general here. The function in general is going to look like the following. So you have one function here that's called h, that is a function of your input, and it's in front. It's a deterministic function of your input. And you also have a normalization factor. So this is kind of a factor in front of it. You see that here comes a vector. So this is a vector, right? We are mapping this to a some dimensional space. And this is the vector. Now, it's a bit, you have to pay a bit of attention. So inside this vector, you have L different sub-vectors. They're all concatenated after each other, okay? So you see here this, where the F, this is F1, and then F2, F3, F4, and so on until FL. Okay, so you have all these sub-vectors. It doesn't matter ultimately, you just concatenate them all, but it's important to just keep in mind. Within each of these vectors, within each of these subvectors, you always have the same repeated term. Okay, you have this W times your X, so the inner product between W and X. You can see there's W1 through Wm, or omega. I think it's an omega. And again, in each subvector, you have this repeated. So what are these omegas, first of all? The omegas are random vectors drawn from some distribution. Now, in practicality, this is going to be a normal distribution like this one here, an isotropic normal distribution. So, and the other part here is what are the Fs? So the Fs, F1 through FL, are going to be functions, deterministic functions. So in an example they gave right here, F1 is the sine function, F2 is the cosine function. And then you have to specify H, and H in this particular example is 1. But it can be a function of X. Here it's just the identity. Sorry, not the identity, the constant function 1. So let's break this a little down. So we have X, and X is going to be a vector. X, as I said, X is going to be like one of the queries here, or one of the keys here. One of them, right? One column or one row, however you conceptualize it. And we wonder, how do we want to map? So x is going to be some vector, okay? Then, this is an ugly vector. Let's draw it like this. X is a vector. Then what we're going to do is we're going to take a bunch of omegas. Now, it's important that the omegas are random, so they come from this isotropic normal distribution, but they're going to remain the same throughout the algorithm. There is a method to resample them, but just conceptualize that at the beginning of the algorithm, you choose these omegas and then you fix them, okay? So the omegas are going to be also vectors, which are random, just a bunch of random vectors, okay? Let's take 3. What you're going to do is you're going to compute the inner product between your x and each of the omegas. So the inner product between your x and each of the omegas. So this gives you omega 1x, omega 2x, omega 3x. So the inner product, this is going to be numbers. Okay? And then you're going to have a collection of functions. So these are going to be functions, maybe function 1 is going, maybe here the sine function, function 2 is going to be the cosine function. Okay. Now you are going to take to make a table, you're going to take each of these products you computed and put them through each of the functions. So this is going to be sine of omega 1x, cosine of omega 1x, sine of omega 2x, and so on, okay? And then you're going to take this table and you're going to flatten it to a big vector. So sine omega 1x, cosine, or no, sine first, the ordering they do. It doesn't matter, as long as you always do it the same, omega 2x, and so on, right? Until you have here cosine of omega 3x. So that's the vector they're constructing, and these are those random features, okay? So this here is going to be the vector that you're constructing. What you do is basically geometrically, your x is like somewhere here. And it's a bit hard to draw in low dimensional space because you don't get the intuition. But if this is your x, you're going to choose a bunch of these omegas. These omegas are going to be randomly sampled from a uniform Gaussian. So this is omega 1, maybe omega 2, omega 3, omega 4. And you're going to compute the inner product between any of the two, okay? So you're going to be essentially computing the projections onto each other, or the angle, however you want to conceptualize it, the angle of this to each of the two, of the omegas, and then you're going to make features out of these angles, right? So this will sort of tell you how your vector stands to each of these random features. Now, the reason I say it's difficult in low dimension is because now I have more omegas than the dimensionality, which is 2 right here. And this makes no sense, right? As soon as I have 2 vectors that are not collinear in 2-dimensional space, I can, if I project x onto them, like this, like if I project x onto both of them, I already have x fully represented, right? There's no need to have more of them. However, if you are in super duper high dimensional space, and you don't have as many features, then you get some interesting approximation properties. Namely, so this was an example, right? We don't always have the sine and the cosine here. This is purely an example. You can only have one function. You see, like this f1, you don't need 2 functions. You can have one, you can have many, okay? And you can choose how many omegas you sample. That is a parameter. So, yeah, you have a couple of choices. I want to make it clear. The choice of h, so the choice of h and f, they go hand in hand. The choice of h and the f's determine what the phi function is, okay? So the choice of h and f determine which kernel function this phi function corresponds to, okay, if you construct it like this. So by choosing the correct functions, you tell the function which kernel you would like to approximate. And then by sampling the omegas, the more omegas you sample, the more accurately you approximate that kernel. Okay, and then you can give some approximation guarantees, as they say. So the softmax kernel is given by this thing here, which we've already seen, okay? And now how do we approximate the softmax kernel? And they show that right here. The softmax kernel is approximated by this thing right here. So it's a bit of a ugly formula, and it contains this Gaussian kernel, the Gauss kernel. So they say if we choose h equals to 1, so just a constant factor, and this f1 and f2 to the sine and cosine, and if we choose d, the distribution, to be a normal distribution, isotropic around the mean, this is the Gaussian kernel. And then we simply have to choose h differently, this factor in front, to make it into the softmax kernel. So as long as we put this factor in front, you can see that this here represents an inner product, right? So you have to kind of think of decomposition. So if you put, you can see f1 the sine, f2 the cosine, which is this, makes it the Gaussian kernel, and then this factor in front of it here, 2 for h, this makes it now the softmax kernel. So if we choose h and f like this, then when we map our queries and keys through, if we map our queries and keys through the phi function and then make the inner product between them, okay, like here, that will approximate, depending on how many omegas we've sampled, better or worse, approximate the result as if we had multiplied them first and then put them through the softmax function. All right? So this, you can see how this becomes much easier because we can independently put them through the phi, okay? And then it's just a linear operation which allows us to do our trick where we multiply k and v first and then multiply by q instead of the other way around, which we're forced to do when we apply the softmax. This was a long way to get here, but I hope you're with this. And this is pretty straightforward actually so far. Now renormalization, we can take care of that easily, but there is a problem. And this is, they argue, this hasn't been proposed so far because it doesn't work like this. So even though you approximate this kernel fairly well, it's a bad approximation. And they say here, there is, however, a caveat here. The attention module from 1 constructs for each token a convex combination of value vectors with coefficients given as corresponding renormalized kernel scores. That is why kernels producing non-negative scores are used. Applying random feature maps with potentially negative dimension values leads to unstable behaviors, especially when kernel scores close to 0, which is the case for lots of entries of A corresponding to not relevant tokens, are approximated by estimators with large variance in such regions. This results in abnormal behaviors, e.g. negative diagonal value renormalizers, and consequently either completely prevents training or leads to suboptimal models. So what they're saying is that when you use softmax, you always get positive values, right? So if I have a bunch of vectors or a bunch of numbers, this is, positive number, negative number, very positive number, negative number, and I run it through a softmax, I will get out a distribution, right? Like this. or really big, sorry, the softmax will scale that up. I will get out a positive distribution, like a kind of a histogram, okay? And now I'm trying to approximate this by this formula right here. And you can see these are vectors, which gives me sine and cosine coefficients. And I linearly multiply two vectors together, which definitely means I can get negative entries and so on. So the renormalization then has to somehow maybe take care of that. And it says especially around 0, when the original softmax matrix would have values close to 0, this approximation is really bad and has high variance. And they also argue a lot of attention vectors are close to 0, because we know that attention is sort of sparsify just by the fact of how the softmax works. It exaggerates the largest inner products and it really dampens the low inner products, okay? Actually, I might not even have done this correctly here if it's very negative. I'm not sure. In any case, they say that's why this doesn't work, because it has such high variance. It's a good approximation, but has such high variance in the wrong places, namely around 0, where most values are. So they call this the softmax approximation with M sampled features, trig, because it uses these sine and cosine functions. And now they're trying to remedy this. And for that, they propose a different decomposition. So a different approximation to the softmax kernel. And they say we can also decompose the softmax or approximate the softmax kernel with the following formula. And I'm not going to, they have a proof for this, but this is the formula. You sample these things, and then you perform this is the inner product that approximates the softmax kernel, okay? And this is further, you can reduce this to this thing right here. So it's a deterministic matrix right here, this, which is given by that, and it's this cos h. So cos h is the hyperbolic tangent. So cos h of x is e to the x plus e to the minus x divided by 2. Okay, so this function approximates the softmax. And that's just something you'll have to take from their proof. However, you can now see that this can be fairly easily represented as an inner product. You already see it here, right? This is the part that comes from x, and this is the part that comes from y. If you want to note this in our notation earlier, again, we use the distribution that we sampled the omegas from is going to be a normal distribution. And our functions are going to be, this h function is the pre-factor. It's simply going to be the made up of the norm of x and put through the exponential function. And then we have two options actually right here. I don't even know why they put the first one, but the second option makes more sense. And there's a bit of more of a factor right here. So you have two functions. There is exp of u and negative x and exp of negative u as the two functions. You remember this is where we had sine and cosine before. Now we have exp u and negative x, exp of negative u. And we can quickly check that this gives us the same thing. So these h functions, if we inner product them, that's going to be to give us this, what is that even? Lambda, is that a big lambda matrix right here? And our vector, let's just say we sample one single omega, right? So we have our x, we sample one single omega, so x is going to give us a vector with two subvectors, right? Since we have two functions. Each subvector is of length 1. So the first is going to be e to the omega x, and the second entry is going to be e to the negative omega x. If we put in y through the same, or as instead of x and y, you can think of queries and keys. That's going to be omega y e to the negative omega y. If we now take the inner product, that is going to give us, and I'm resolving the exponentials already right here. So that's going to give us e to the w x plus y, and here it's going to give us plus e to the w, or sorry, the negative w x plus y. And that's the, there's a normalization factor. That's why the square root of 2 is here, right? So that comes in somewhere here to give us this normalization factor. So this is exactly the hyperbolic cosine of omega times z, and z is x plus y. They say it somewhere. Yeah, here. Okay. So if we choose f1 and f2 to be this x bu and x negative u, then we get, if we perform the inner product, we get out exactly this formula number 7 right here. So this is this, and that is an approximation of the softmax kernel, of the softmax function. It's just a different approximation than before, okay? And the cool thing about this approximation is that the approximation itself only ever has positive values. So these vectors here, you can see the x, the vectors here, and there's of course a factor in front of this right here, which is going to be also an exponential. These are all exponential, so these are all going to be positive features, which is very, very nice. And they also show this theoretically. So here, this kind of funky graphic shows this. This is the ratio of the approximation mistake, okay, the ratio of the approximation mistake of the original approximation that we discussed and this new positive approximation that we just built right now. And you can see that in parts here, it's fairly similar. So this, I believe, so R is the ratio. So it's fairly flat right here. But there are parts where it just shoots up, right? And in fact, they can prove that, you can see this also right here. So the error of the trig approximation just shoots up, while the positive approximation just stays flat or flatter in these regions. They can in fact prove that the error of the, so you see the error if the softmax values go to 0, so that's the problematic regions. The error of the trigonomic approximation can go to infinity, while the error of the positive approximation goes to 0. Okay, they have a number of theoretical results in here. I think that's one of the main ones. The fact that this approximation succeeds where the other approximation fails. Really quickly, they also have this variant here where they don't build a vector of two subvectors, but just one with just the exponential function. And that is the same thing because, of course, if you sample w, you're going to have, omega. If you sample omega, you're going to have omega as much as negative omega, I believe, and thereby, in expectation, you're going to get this hyperbolic cosine again. I think that's the reason why, but this lower construction here gives you the hyperbolic cosine. Okay, so pretty cool. We simply use this approximation. We run our queries, right? Our queries and our keys through this. And again, we ideally use more omegas than just one, maybe a bunch. The more we use, the better. We obtain a linear function that approximates the softmax function. The more we sample, the more it approximates, it's unbiased, and so on. They have a bunch of variants of it. So variant where you normalize the omegas, which gives you the regularized softmax kernel, which is not a softmax anymore, but it's a regularized softmax, and they can approximate this in pretty much the same way, except instead of a normal distribution, you use a uniform distribution right here. And they have a bunch of other things, namely, one other improvement is that so far we've simply sampled these W's, okay? We sampled the W's from a normal distribution, like this here. They say we can improve even further, namely we can strictly improve. With, this gives us an estimator with strictly lower variance if we make sure that the W's we sample are exactly orthogonal. So they're already approximately orthogonal if we sample them from a high dimensional space, but if we make sure that they are exactly orthogonal, then they are giving us an even better approximation. And you can do that by this procedure called the Gram-Schmidt or orthogonalization or Gram-Schmidt renormalization procedure. It's a pretty easy procedure, and it doesn't mess with your unbiasedness whenever D is an isotropic distribution. Isotropic just means the same in every direction. So like a standard Gaussian would fulfill, or a uniform would fulfill this thing, as long as it's centered. I think maybe even if it's not centered, depends on how you renormalize. Okay, this is irrelevant. But if you make them exactly orthogonal, say this leads to the first theoretical result showing that orthogonal random features can be applied to reduce the variance of the softmax or Gaussian kernel estimators for any dimensionality D, rather than just asymptotically for large enough D, as it is the case for previous methods, and leads to the first exponentially small bounds on large deviations probabilities that are strictly smaller than for non-orthogonal methods. Okay, so you're going to end up with a thing that's strictly smaller, so bounds that are strictly smaller than if you don't use orthogonality. The only thing it requires is that M is smaller or equal to D, so the number of omegas you sample is going to be smaller or equal to the dimensionality that the original space operates in, which let's say this will be the case in all our experiments. Okay, and again, these are exponentially small bounds, which is pretty cool. I guess for you, the end user, it matters that this works, and if you use all of their tricks with the positivity and the orthogonality, so by the way, this here is where they show that, see, the orthogonal MSE, the mean squared error, is smaller than the original one minus something. And as long as the something, of course, is greater than 0, you're going to have something that's smaller. Okay, they prove a bunch of other things, again, about this kind of, this regularized, sorry, not regularized, I forget, it's the, where you divide by the norm. In any case, they implement this in JAX. Oh, great. Wow, cool. I have no opinion on JAX, but they have the code released, and I'll of course link to it. And here you can clearly see, so this is a log-log plot where you have L, the size of the input, and the number of seconds that it takes to go forward and backward over here in the model. And you can see the X here. The X is the baseline, where you simply bypass the attention matrix. You simply take the identity function and just return the value matrix. And you can see that the performers, they scale fairly well with that baseline. And in fact, they scale at the same slope, which is the important part, right? Here you can really see that this is linear slope, where the transformers, which are the dashed lines, they all curve upwards, which of course is that quadratic requirement. the same in the backward pass. I don't know if they continue curving. I think it's also a straight line in the log-log plot, but the slope is 2 instead of 1, like the linear models. Again, the comparison is only important between the baseline and the lines that you're looking at. If they have the same slope, they scale the same as you get higher. And look at that. This is log L, right? So these are now 2 to the 18th tokens, and I believe this is done on 1 GPU. Yes, so an out-of-memory error on a V100 GPU. And this is pretty good. This is pretty good news for everyone who wants to run the performers in kind of a low resource environment. With low resource, I mean like a deep learning GPU instead of 1,000 TPUs, which is pretty cool. They also show that their method is better than so the orthogonality is better than the IID features, and then of course the positive IID features are better than this original trigonometric decomposition. And they show that this thing that you can take a transformer checkpoint and you plug it into the performer, and you simply have to fine-tune a little bit to get it to the performance that the transformer was at, right? I believe this is the original training curve of the transformer. So, it's not a fair comparison because the performer starts from the checkpoint already. At least that's how I interpret it. It's not clearly written. And they say, okay, over here, this trig thing works. This is the original approximation. This even works. However, if we do that on a bit more challenging, more longer sequences data set, then you can see that the trig softmax, it just whacks out. That's this thing here. And you actually need these positive approximations. And that compared to the linformer here, which is pretty cool. So the linformer, I've made a video about it if you want to know about it, but they also do random projections of the attention matrix. But you can see that the linformer plateaus along with the performers if you don't redraw the random features. So if you want in the performer, if you do it at the right time, you redraw these random features, these omegas. You have to see where you can't just arbitrarily redraw them between computation steps, but at the end of like a computation step, you can redraw for the next computation step. And if you do that, and even better with the regularized or the normalized features, you get to the same level of performance that a standard transformer would get, but of course without the quadratic requirements. And okay, lastly, as I said, they've already swapped out this nonlinearity by a ReLU. So here they construct a performer ReLU, taking f equals ReLU in equation 5. You remember what f was? F was the sine and cosine when we had the first approximation, and f was the exp of u and exp of minus u in the second one. And as I said, the big improvement in deep learning came when we swapped sigmoids for ReLUs. And here they're already trying swapping now this, because they say, well, so we have a method that we can basically plug in anything we want. So they plug in ReLU because it's, worked well. And this, again, it works pretty well. So they compare also with the reformer here, with the linformer, as you can see. And of course, they beat everything. Now, whether or not this method is going to be the next thing, like the thing that everyone uses, we don't know. It's fairly possible. It's pretty cool. And it appears to be theoretically solidly grounded, but you never know from the experiments of the single paper. The broader impact statement, much respect. They just use it to tell you how awesome their paper is. Like, there's no mention on on any kind of ethical impact, which I believe, like, I'm all for these kinds of broader impact statements, like just kind of, okay, research on transformers is going to be better because now people have access to it, it's backward compatible, that's pretty cool. It's applicable to biology and medicine because we can now take longer sequences. It's all like, yeah, I like these kinds of broader impact statement. The last thing here is that you might be so the only problem is if you want to do this causal attention, that if you want to do like a generative model, like a GPT sort of model, you have to do a bit of a trick. And that is because your attention matrix isn't a full attention matrix, right? So you can't just decompose it. It's this lower triangular matrix right here. But since you have linear decomposition of this thing, you can do these kind of prefix sums. Namely, you can compute simply, so you can compute the key 1 times value 1, and then you can compute key 2 times value 2 plus key 1 times value 1, and you compute key 3 value 3 plus key 2 value 2 plus key 1, value 1, and so on. You compute these things, and these are all the big where the L goes away, right? So we do that first, and then we simply have to come along and we take Q1 multiply by Q1 V1. We take Q2 multiply by this and this. Q3 will multiply by this, this, and this. And you see, that's how you get your causal attention. So you simply keep track of these prefix sums right here. And then when the next Q comes along, you simply multiply it by all of the things that are above it in the prefix sum. That's how you get your triangular matrix. So even that is solved. A thing that I believe the linformer wasn't able to do with its particular decomposition. I might be wrong here. All right. They have a bunch of experiments on protein analysis and so on, which of course wasn't possible, I guess, before because it was so heavy. They also have like ImageNet 64, as you can see right here, which is an impossible data set for a classic transformer. As I said, they have code. Code is in JAX, which is like, it's ugly code. Let's be honest, but it's code, so that's fairly cool. And I want to point out right at the bottom here is actually where the stuff happens. So you can see that just quickly, you have here keys and queries are, where is it? Exact. So the queries and keys are going to be constructed right here. So query prime and key prime are going to be pulled through this feature creator, which implements these kernels. So these can be either, as we said, these exps or the relus or the sine, cosine, whatnot. Then you're going to multiply the queries and the keys, which gives you this W matrix. And all that we need to do now is normalize it. Okay, so we renormalize by constructing this denominator right here. And then there's a whole block for the unidirectionality, which you can imagine is pretty ugly, but the renormalization, we constructed, reciprocal means we take the inverse, multiplied by the W and return the result. This should be translatable into your favorite whatnot, PyTorch or TensorFlow. Maybe it's already been done. I haven't researched that particular thing. In any case, I invite you to check out the paper, the code, play around with the functions used here. As long as you use you don't need to know. Like these papers, they always know which kind of kernels their functions correspond to, but in SVMs people just went nuts. I just plug in some functions, see what happens. Probably nothing good, but it's possible. All right, so that was it for the performer. I hope you gained something from this, kind of an understanding of how it works. and I wish you the best. Bye bye.